All right, so in this lab, what we've got here is we've got an unknown solution of hydrochloric acid. We don't know what it is. We've got 20 milliliters of it. And what I've got over here is I've got a burette, once again, set up with 0.2 molar sodium hydroxide that is here. And I've just got it in some water with some universal indicator that is there. And then what I'm going to do is I'm going to go ahead, I'm going to add in my acid to this solution. And obviously you can see that it turns red, which is what universal indicator does in an acid solution. And my pH probe should now be reading quite a low pH, and it is. And so what I'm going to do now is I'm going to titrate this and keep track of my volume of how much I add and what the pH is at each of those particular volumes. And I'm going to develop a titration curve where I have the individual spots set and ready to go, the individual data points, knowing what the pH is at the particular volumes. And once I am all set with all of my data, and I have taken this through an entire spectrum of the titration curve from the acid side of things over to the basic side of things, then I should be able to figure out what the concentration of my unknown solution was that I just added in here. So now I've run through my titration, and you can see that my level here has dropped, and I have gone all the way from red to purple. So now what we need to do is look at the individual data points and see where exactly the pH changed, where the equivalence point is, and once we know where the equivalence point is, we will be able to figure out what the concentration of that acid was. So this here is a look-see at the representation of the data that I collected here. And what we can see is that with a strong acid, strong base situation, you are going to see at a pH of 7 where the equivalence point is. And sure enough, that looks to be pretty darn close here to the inflection point of our curve. And the whole idea of that point right there is that the moles of the acid and the moles of the base are equal to each other at that point right there. So at that point right there, the moles of the acid and the moles of the base are equal. So to do the math on this, because they're both solutions, it's real simple. We're just going to do MAVA. We know the molarity of the acid times the volume of the acid will give us the moles of the acid, and then that's going to be equal to over here the moles of the base, which is going to be MVVB here. So I had 20 milliliters of my unknown hydrochloric acid solution, so that's going to be 20 milliliters, and I don't know what the molarity of that is, so that's going to be my X. And then that here is going to be equal to the molarity of my base, which I know to be 0.20 molarity times the volume of the base. And the only thing is I have to pick the correct volume here. And given this information, it looks to be that your equivalence point is, I don't know, should we call it 26, 25? Yeah, it's somewhere around 26 milliliters. Let's go ahead and call it there. So then all you got to do at this point is some quick algebra ification. So this is 0.2 at 26 divided by 20 looks to be about 0.26 molarity. So the molarity of my unknown acid was right at about 0.26 molarity. So all you have to do for solutions such as this is remember that the moles of the acid equal the moles of the base, and the easiest way to do that is just MAVA equals MBVB.